Hello everyone, welcome back to Exploring Quantum Physics. We're now going to proceed on the work done in the previous lecture and start applying it to problems of atomic structure using the old quantum theory, and then work on towards new. Once again, let me remind you of the relevance of Bohr's original paper to the discussion that we're having today. So to remind you where we left off at the end of the last lecture, we solved the problem for the motion of the hydrogen-like systems, one electron, one nucleus. In classical mechanics, we found a sort of generic, fairly simple solution. It allows for any value of the total energy, any real value of the total energy. When that energy is negative, the orbits they're not only bounded, but they close on themselves. It's a very non-generic fact in dynamics. And when they are when the energy is positive, then they travel off to infinity. Now, I strongly encourage reading this paper, which is contained in the additional materials. I mean, not from start to end, but just to get a sense of the great thing that it accomplished. And you have to go rather far down into the paper, and this is one of the homework problems, is to go find and analyze the language that is used in this section. And we give some hints as to what page to look at in the guidance to the homework. And the fantastic thing that Bohr did that still survives as a foundational idea is that it's the quantization of angular momentum. So he found the series of circular orbits that he thought should be stationary states, and he actually sort of mentions this almost as an afterthought, that the selection criterion that he used amounts to requiring that the angular momentum assumes an integral value of the reduced Planck's constant h bar. So you see, when you do that, you get an instant solution for the discrete energy levels. So you require that the angular momentum be an integral multiple of h bar with running from 1 to infinity. Now, actually, in modern quantum mechanics, the value 0 is allowed as well. So let's be very clear about that. But in any event, here's an expression for the energy levels, which I've cast it here in sort of modern form. Alpha is the so-called fine structure constant. Again, the definition depends upon the choice of electrical units. You might see a 4 pi epsilon naught in the denominator, depending on the choice of units. But in any event, the fine structure constant is a pure number. It's approximately equal to that. And so if you want a mnemonic for remembering what the Bohr energy levels are, it's kind of like E is equal to mc squared. So all the dimensionality of energy that appears in this expression is due to the rest mass energy of the electron, Einstein's rest mass energy, and then the coupling constant. This is a pure number, z alpha squared over 2n squared. I'm going to phrase that in a slightly different way in the inline quiz. Have a look and see if you come up with the same conclusion. So the Bohr energy equation gives rise to a very important fundamental constant, one of the most accurately measured, the so-called Rydberg constant, which takes this value in units of inverse meters. And so the energy levels of the hydrogen atom can be conveniently expressed in complete dimensional form in terms of the product of the Rydberg constant and Planck's constant and the speed of light. And this number, R infinity hc, is approximately equal to this number in electron volts. That's the energy change that you get by moving an electron through a potential difference of 13.6 volts, about the voltage of a car battery. Now, another thing that falls out very nicely from the Bohr theory, and this, at least this type of scaling is retained in modern quantum mechanics, is the relationship between the radius of the orbit and the so-called principal quantum number. So the radius goes as the square of the principal quantum number, and the coefficient of proportionality is the length of the Bohr radius, which takes this value. It's I guess you'd say that's 53 picometers approximately. Now there's another important relation which I'll just let you discover in the inline quiz. So the virial relationship that you got through working through the inline quiz, again, the constants of proportionality that connect the total energy with the expectation value of the kinetic energy and the potential energy. Those are preserved in modern quantum mechanics. Now, well, we said Bohr had a great breakthrough. What's the basis for that judgment? One was just these spectacular agreement with experiment. So again, the frequency of the spectral line, the inverse of the wavelength of the spectral line, is given by an energy difference, and so it was possible to compute all the possible energy differences according to the Bohr formula. And this, as we shall see, gave an account of all the known lines of hydrogen, solved some other problems, and